Hey guys, in this video I'm going to show you how to calculate a net charge on a peptide or even in a single amino acids at different pH solutions. So let's suppose I have this sequence here that contains lysine, serine, valine, and glutamate here. If you're not told which side is an N terminal and which side is an C terminal, it's typically the left side is considered the N terminal and your right side is considered the C terminal unless they state to you otherwise. Let's go ahead and actually draw it out, and you don't necessarily have to know the exact structures of these amino acids if you're just trying to figure out the net charge. But I'll show you the net structure of this particular peptide here. And if you don't know the net structure of amino acids, you can just get away with having the knowledge of which ones are polar, basic, and acidic. So let's start with lysine here. So I'm going to go ahead and start those, make those in the protic form or protonated form. So I have the NH3 here, and I got a carbonyl there. And the side chain of the lysine is actually in a basic. So I want to go ahead and draw in a basic form of that. So this contains actually 4 carbons, and on the bottom you can have an NH3 plus there. And you get this one peptide bond here, and then you're gonna get your next sequence on the line, next amino acid, which is the serine. So it's gonna start out with the NH there, and then serine actually is just gonna be CH2OH on the R group. And then you have the C terminal of the serine, and then you're going to be making a new bond, or that's like going to be a peptide bond, and then you're going to have this valine connected. Now remember that's got the NH there, and on the valine, remember that's just an hydrophobic. It's a small chain on the valine. It's just got an isopropyl group, basically, C terminal. And then I'm going to go ahead and draw another peptide bond here, or the amide bond you can say, and then you got the glutamate at the end. The glutamate acidic side chain, which actually contains 2 carbons, and then you're going to have an OH group there. So I got a combination of both a basic and acidic, and I got some polar amino acids here. That's serine, and I got this nonpolar valine is here as well. Just let's go ahead and finish off this full molecule here, full compound here. That's going to have the C terminal. That would have the OH on this one. So when I look at this, sometimes they ask you questions where like how many peptide bonds you have. So if you're dealing with 4 amino acids in the sequence, you're going to have 3 peptide bonds. You got one of them right there, you got another one right there, and you got another one right there. So you got 3 peptide bonds. And now I'm going to be focusing on the amine group. So I got an amine group on the left side here. I got an amine group on the right, on the bottom right there. I don't really have anything else going on. This serine has an OH, but that's not really going to be affected by the different pHs because the pKa of alcohol is like over 16, so we don't have to worry about it. Valine don't have any acidic or basic side chain, and then I got to worry about the acidic side chain that you got on this glutamate right there, and then also the C terminal of this whole peptide. Now let's suppose if you did not know the structure of these guys, but you still knew what their natures are, whether which one is acidic or basic or polar and all that, you can still answer that question based on that. So let's say I got an lysine here. So I know I'm going to have a C terminal or N terminal on the lysine, so I'm going to go ahead and draw out an NH3 there. And eventually I'm going to have a side chain of that lysine that's going to have the NH3 attached to it. So that's how you want to think through it. And then I got a peptide bond made with the next one and the line, which is going to be the serine. Now serine, I'm just going to go ahead and write down the S for that. The side chain of serine just eventually going to have an OH there. I'm not drawing the full side chains, just knowing what particular type of side chains you got in there, whether it's acidic, basic, or neutral, or anything like that, so that you can only focus on that. So this is when you actually maybe trying to figure out the pH or the net charge on a peptide where are kind of running out of time. So then you don't want to draw the full structure, but just know what the side chains kind of entails in that case. So you got the serine right there, and then the next one that's going to be in the line. I'm going to go ahead and draw a peptide bond here, and then we got valine. Valine is just an R, so nothing going on the valine. I'm just going to write down R because it's an hydrophobic chain. And then finally, I got the glutamate. So then I'm going to go ahead and write down E there. Now, glutamate actually has an acidic side chain, so I'm going to go ahead and write that down as COOH. And then also don't forget your C terminal, so COOH as well. So you can just answer that question based on this sequence as well, or you can just go and draw the structure if you know the structure, but if you don't want to waste your time, just know what the acidic or what the side chain natures are for those different amino acids. Now, what their pKa's are, you got to know the rough ranges of the pKa's. Now, N-terminal pKa is typically going to be anywhere between 9 to 11. We don't know exactly what those going to be. That's just the rough range on those. And whenever they are in a peptide form, they are individual pKa's, and when they are in the peptide form, they may not match exactly. So there may be minor changes in their pKa's, but the pKa change is not going to be too much. So I can still say, okay, I'm going to be in the range of 9 to 11 here. The side chain pKa for the lysine is about like 10.5. So it may change a little bit because it's in the peptide form now, but it's not going to change dramatically. It's probably still going to be somewhere around 10-ish, I would say. Okay, coming down here on the C terminal pKa runs anywhere between, I would say, 2 to 3 on average because it's an acidic, and then the glutamate side chain pKa is about 4-ish, 4.2. So it's still going to be around that range. It may not be exactly 4.2 because it's in the peptide now, but it doesn't really matter, all right? So because we got this in, um, we want to make sure we have the range as close as possible. And even if it changes from 4.2, it's not going to be like, changes to 7 or anything like that. It's probably going to be a few points or a few decimals off from 4.2. So let's go ahead and come down here. I'm gonna write down, let's say it's roughly 9 to 11 here. It's approximately 10 here, approximately 2 to 3 here, and I'm gonna say approximately 4.2 here. So if I'm asked what's gonna be the net charge at a pH of, let's say, 1. So when the pH is less than the pKa, that means you have more acid. It's a very acidic solution. Then in that case, everything is going to be protonated. All right, anything that's going to have a pKa that is going to be greater than the pH of this particular number 1, all those things are going to be protonated. So you can see how this NH3 is going to be protonated because its pKa is between 9 to 11. This NH3 on the lysine side chain is also going to be protonated because its pKa is a lot bigger. Then I can also say this side chain of glutamate is also going to be protonated. And then this C terminal is also going to be protonated because we're looking at the pKa range of this anywhere between 2 to 3. So everything is going to be protonated. Everything is going to have protons on it. And another thing you want to think of it, whenever you are becoming more acidic, that means whenever your pH goes down, your H plus concentration goes up, then you tends to become more positive. But now, how much positive? That's you have to look into there and calculate the charge, but it's just kind of in a general idea that when the pH goes down, your hydronium ion concentration goes up, which means the H plus goes up, so that means it actually becomes more positive. Now here, you gonna have everything protonated. I don't have any charge on any of those carboxyl groups or acid groups there. So then I still gonna have a charge on both of these NH3 groups. So then at the end of the day, your net charge is gonna be +2 then. That's how you wanna look at it. All right, let's look at maybe another range. I'm just gonna copy this down here. maybe I can say a pH of, let's say, 7. When the pH is 7, I got these groups right there with an pKa of anywhere between 2 to 3 and pKa of 4.2. They are now gonna start losing their protons because your pH is over the pKa value. So anytime the pH goes over the pKa value, you're gonna be more basic for those particular groups. So I'm gonna end up getting this. I'm gonna go ahead and lose that hydrogen there, lose that hydrogen there. This starts becoming a negative here, and this will become negative as well. But then when you look at your NH3 groups, your NH3 group's still going to stay protonated because their pKa's are still higher than the pH, or another way of saying the proton or this solution of pH of 7 is not basic enough to remove these protons, so it will still stays those protonated. So when you have those protonated, the net charge in this case now, I'm going to have plus 1 from these NH3 groups, but then I got minus 1 and minus 1 from those carboxyl group or the acid carboxylate groups right there. So since when I calculate all that out, it turns out to be a 0, a net charge in this particular case. You can also have a situation where maybe you have a pH of, let's say, 12. If the pH of 12, now this solution is very basic, so it's going to remove all the protons that has a lower pKa value. And turns out every single thing is actually going to have a lower pKa value. So I'm going to be losing the proton here. I'm going to be losing the proton here. And as a result, will end up having only 2 protons left here, 2 protons left here, 2 hydrogens left here. And you lose the charge on the nitrogen after that. So since you lose the charge on the nitrogen, um, becoming more negative now. So when your pH goes up, you can say your H plus concentration goes down or your OH minus concentration goes up. Then if your OH minus concentration goes up, that means you are becoming more negative in this case. Now, how much negative, that you're going to have to look at their pKa values roughly to figure out how much negative they're going to become. So when you're looking at the net charge here, I got 0 on those amine groups right there, but then I got a minus 1 on this carboxylate group here, and I got a minus 1 on this carboxylate group here. So then your net charge at the end of the day is going to be minus 2 here. So the take-home message on this one, remember, when your pKa is greater than the pH, you stay protonated. And if your pKa is less than the pH, which means you are more basic for that particular pKa group, then you are going to be deprotonated. Okay, and when you have a pH equals to the pKa exactly, then in that particular case you can say you're going to have you're going to have equal amount of protonated versus deprotonated. So amount of protonated and the deprotonated is going to be exactly the same. So then in that case, you can say the positive and negatives are actually equal to one another, but that's typically not the case that you want to looking at. You are either going to be having a higher pH or a lower pH than the pKa values, and this is how you want to look at it. So when something is at a lower pH or staying protonated, that means you are going to be relatively more positive. And if you are becoming deprotonated, you are going to be relatively more negative. Okay, so this is how you're going to be calculating the net charge on a amino acid or even in a peptide.